So, good evening, good afternoon to one and all. Thanks for inviting me in this wonderful session. So, in last class, what we discussed about quiz kit demo, right? So we are in faculty development program. So it is a series of program which is happening through Andhra Pradesh State Council of Higher Education. I thank APSCHE. Okay. So in association with MNIT, DST, IIT Madras, IBM and CTS. So I thank each and everybody involved in this program. Okay. So in last class, we discussed about introduction to IBM QuizKit, and we have a fair enough about Blocksphere. Today, we're going to see how to install QuizKit in your local machine as well as in Google Colab. And we can use in multiple platforms, how we can use this framework for your benefit. So before that, I try to recall what we covered in last class. We discussed about Blocksphere. We discussed about Blocksphere. So Blocksphere is a unit circle, okay, starting with radius equal to 1. So it is a unit radius. And this sphere is divided into two hemisphere, northern hemisphere and southern hemisphere, because we try to represent two-level system, okay. So what is the two-level system? We try to map with this Blocksphere because we are using binary system. So whatever the binary data we are having, we try to associate with this Blocksphere. Okay, and we are creating three axes, Cartesian coordinate x, y, z. So if you have three axes, you can represent Cartesian point anywhere in this sphere, inside this sphere. Okay, so let's take two extreme points. So this is one extreme, this is one extreme. So this is in northern hemisphere, this is in southern hemisphere. So for whole northern hemisphere, this point is extreme. Okay, for whole southern hemisphere, this point is extreme. So these extreme points are chosen for representing basis state or pure state. Okay, so remember this, we have a sphere which contains radius equal to 1 unit radius. So this is a unit sphere. So this sphere used for visualizing qubit, okay, Blocksphere. Okay, so we are dividing this sphere into two half because we want to represent binary data over here. Okay, so where we can represent binary data in two extreme locations. So North Pole and South Pole, pure states. So this is called K0. This is called K0. So you have a bar and you have a value 0, then followed by greater than symbol. So this notation is called Ket notation, Ket0. So I will write over here. So bar, so this is bar, okay, followed by the value what you represent, followed by this greater than symbol. So this is called Ket notation. Okay, in same way you can represent bar 1 followed by greater than symbol. This belongs to Ket notation. So specifically, how will you say this one? This is Ket0. This is Ket1. So remember like this. Okay. So what we do, we will take a random point inside this sphere, and we are generating a vector from origin towards that point. So this point is nothing but your quantum particle. So this will represent the location of your quantum particle over your qubit. Okay, so imagine this green dot keep on moving, keep on revolving around your Blocksphere. So it will not be a stable one. So it always in random motion. Okay, so wherever the electron is, this state vector always follow like a needle. So it is like a pointer. Okay, so what we are doing, we are getting information about your quantum particle with the help of this quantum state vector. So this navy blue vector is called quantum state vector. If you want to know information about your quantum particle, you need to know where your quantum state vector represents or points out. Okay, so this particular point is called mixed state. So you can say it is a mixed state or superposition state. It is in between K0 and K1. Okay, so previously what we discussed about 2 points. These are pure states, pure. Okay, so anywhere apart from these 2 points is called mixed state. So or superposition state, you can say in quantum terms superposition state. And what we are doing, we are slicing the sphere into x dash and y dash. So wherever your quantum particle is there, you try to slice that sphere. Okay, so from this plane, you are able to generate a projection to xy plane. So x dash and y dash is axillary plane. From axillary plane, you try to project to actual xy plane. Okay, so if you do this, it will do intersection in xy plane. From that point, again, you are doing a projection towards origin. So by doing 2 projections, we are able to get a right angle triangle. Okay, so why we need to form a right angle triangle? Once you form a right angle triangle, you can convert any Cartesian coordinate into polar form. Okay, this is our whole point. Okay, so to convert polar form, we need to have angles. So we confined one angle from z-axis to quantum state vector. So one more angle from x-axis to downside projection. So we got 2 angles. So if you got 2 angles, you can apply trigonometry. Then you can apply polar form. So in previous class, we discussed all this stuff. I just try to recall. So here d equal to 0. D equal to 0 means it will point to North Pole. So recall from previous slide. So if d equal to 0, this vector is pointing to North Pole. So this is the logic. Okay. So this is the wave equation. We got psi equal to cos theta by 2 multiplied with state 0 plus e to the power I psi multiplied with sin theta by 2 multiplied with state 1. Okay. So we have 2 components. 2 components are extreme, state 0, state 1. That is why we are using mathematical form of cos and sine. So cos and sine are opposite in nature. So we are using opposite nature with the help of state 0 and state 1. Right? So apply d equal to 0. So cos 0 by 2, sine 0 by 2. So you will get state 0. So I try to answer the question. The point on the surface, not point on the surface, inside the sphere specifically. So for understanding, I'm representing this way. Good question. So this is not about surface. This is about inside your sphere. Okay. When you do measurement, it will touch surface. Imagine in that way. Okay. So the next scenario, if you try to change d equal to pi, what happens? So you will get state 1. It means it will get state flip. So how we are doing bit flip, we are getting state flip. So it will move from 0 to state 1 if you apply d equal to 0. From state 1, again, if you are applying d equal to 0, it will move back to state 0 in this way. Okay. So this is related to NOT gate. This is related to identity gate. So this is for pure state. Imagine in this way. Okay. So the next interesting example, when you apply d equal to pi, you will get both components. Sorry, d equal to pi by 2, you'll get both components. So if you apply d equal to pi by 2, it will go in between state 0 and state 1. It will lie over exactly in x-axis. So that is why both components are there. State 0 is there, state 1 is there. And what is the magnitude? 1 over root 2. 1 over root 2. So this is equivalent to Hadamard gate operation. So this is equivalent to Hadamard gate operation. So what Hadamard gate will do? It will create equal superposition. Equal superposition. So what is the meaning of equal superposition? Definitely, if you apply equal superposition, it will come to equator. Anywhere in the equator or level of equator, you can say in this way. Then you apply the second angle psi equal to pi by 2. Now what happens? The sine component is get changed. The phase of your signal is get changed. So for imaginary purpose, if you apply d equal to 0, sorry, d equal to pi by 2 from stage 0, it will lie over x-axis. So we'll cover that part. We'll cover that part. Okay. So what happens if you apply the second angle? It will change phase of your signal. Phase of your signal. So it will move from x-axis to y-axis. Right? So this is a phase gate. Now we have three axes: z-axis, x-axis, y-axis. Okay. So this belong to z, this belong to x, this belong to y. Right? So x-axis contains real component. Okay. Y-axis contains imaginary component. So any point inside your block sphere, it is a complex form. It contains both real component as well as imaginary component. Okay. Then we discussed how to represent in a matrix way. So look at the stage 0. So stage 0 located in North Pole. So it is in upper hemisphere, northern hemisphere. So that is why the upper component is 1, the lower component is 0. So in case of stage 0. So look at state 1. State 1 located in South Pole belongs to southern hemisphere. That is why the lower component is 1 for state 1. Okay. So in this way, you can physically relate how you can represent in the matrix form. So look at the positive. So positive exists in the equator. So it belongs to both hemisphere. It belongs to both hemisphere. That is why it is represented with 1, 1. Okay. So what is the magnitude of state, positive state? So 1 over root 2. So we'll discuss this, why we got 1 over root 2. So in the same way, if you want to represent negative state, which is opposite side of this positive state. So that is why we are representing negative sign to depict opposite side only for the second element. Okay. So in this way, if you are able to recall everything, you can easily able to remember. So look at the I, state I, which is nothing but y-axis. So this is like positive y, right? So positive y, the second component is I, because y-axis represent imaginary axis. Okay. So same way, if you want to represent minus I state, the second component is minus I. So whole form you can see in this way. So 0, 1, positive, negative, plus I, minus I. So this is what we discussed in last class. So I'll share this link again. So always try to attend with your laptop or CPU. Don't attend with your mobile. So you cannot practice. So look at the chat box. So go to this link. So last class also we shared. We practiced little bit. So all of you go to this web page. So I try to narrate. You watch side by side. Watch side by side. So here these two are pure states. These two are pure states. State 0 and state 1 are called pure states. We already remember from the block sphere. Okay, the same idea. So if you want to prepare qubit, either you can start from 0 or start from 1, state 0 or state 1. Okay, so if you click X, what happens? It will do NOT operation. So X gate is equal for NOT gate. Okay, then Y gate is equal for NOT gate plus pi by 2 rotation. So remember, I start from state 0. If I click X, it will move to state 1. From state 1, once again, if we click X, it will go back to state 0. So if we apply 2X gate next to next, which will cancel each other, go back to original state. So what I did, I applied X gate from state 0. It went to state 1. Again, I apply X gate from state 1. It will go back to state 0. So this is original state, right? We started from original state. It went back to original. So 2X gate will cancel each other. It means X gate has its own inverse. So same way you can check with Y gate. Start from 0, click Y gate. It will move back to state 1. But you can see the difference over here, downside, phase difference. So physically you cannot see in block sphere, but signal wise little difference is there. So pi by 2. So this Y gate have special ability when compared to traditional NOT gate. So in traditional NOT gate, you cannot see this difference. So this is the advantage in quantum. So whenever you see any quantum gate, it will have additional advantage when compared to classical gate. So Y gate is quantum gate, where X gate is not quantum gate, it is traditional NOT gate. So remember this. So Y gate is quantum NOT gate. Yes, you can see if I want to show some difference, I can change some phase. If I apply X gate, it will do bit flip or state flip. But if I apply Y gate, it will have additional information. Not only the bit flip, I can vary some information. Now I can represent pi by 2 phase difference. So more colors you have, more combination you can produce. Okay. So how many degree of freedom you have, that much different data you can represent. Are you able to get the point? So in traditional way, you can represent 0. Okay. You can represent 1. But here I can represent 0. I can represent 1. But I can represent in 2 ways. 1 and -1. So I have additional degree of freedom. So this is changing phase. Are you able to get the idea? So here we are not able to produce -1 instead of in between. So it is not pure 1. Additionally, we have some information, pi by 2 phase difference. I will explain what is the use. I will explain one by one. Again, click Y from state 1. It will go back to state 0. Okay. Now look for Z gate. Apply Z from state 0. So apply Z from state 0. The state remains same. So Z gate will act like identity gate. So it will do nothing. So Z gate will do nothing from state 0. Okay. So what do you do? Click state 1. Click state 1. Apply Z gate and observe what happens. So from state 1, apply Z gate, observe what happens. It will move to -1 state because we have pi rotation. Pi rotation means this is positive side, this is negative side. Now it is pointing to -1 state. Physically you cannot see, but in phase difference you can able to realize. Are able to get the point? So Y gate, what it will do? It will introduce pi by 2 rotation. Okay, what Z gate will do? It will introduce pi rotation. So that is why no sign changes happened over here. No sign change because we implemented only pi by 2 rotation. But in case of Z, we applied full rotation. So sign will get changed. So Z gate have additional advantage when compared to classical gates. So you cannot implement Z gate in classical. X gate you can implement, but YZ you cannot implement. So all of you able to follow? So next what we do? We try to look over Hadamard gate. So click stage 0. All of you click stage 0. Apply Hadamard and observe what happens. So what we did? We are in stage 0. We applied Hadamard gate. We changed to positive state. Positive state exactly in the equator. Exactly in the equator. It means we created equal superposition with the help of Hadamard gate. So it is 50% away from 0. Okay. Also it is 50% away from state 1. So that is why Hadamard gate will create not just superposition, it will create equal superposition exactly in the equator. Okay. So now what you do, apply Hadamard gate from positive, it will go back to stage 0. So we covered 2 examples. Okay. From stage 0, we applied Hadamard, it went back to positive state. From positive state, we applied Hadamard, it went back to stage 0. So applying 2 Hadamard gate next to next will cancel each other. Now, interesting question. Okay, click state 1. Click state 1. Apply Hadamard gate and observe what happened. So we are in state 1. From state 1, we applied Hadamard gate. We went back to minus state. So this is opposite of applying Hadamard gate over stage 0. Are you able to compare? So if you apply Hadamard gate from stage 0, it will go to positive state. Equal superposition. Okay. If you apply Hadamard gate from state 1, it will go to negative state, but both are equal superposition. It is in equator, right? It is in equator. So this make distinction between where you applied Hadamard gate. Okay. So you can clearly understand based upon your position, what is the previous state of your Hadamard gate. Suppose if you are in minus state, then you can imagine you applied Hadamard from state 1. If you are in positive state, then you can imagine the previous state is stage 0. Then you can predict from negative state, if you apply Hadamard, it will go back to state 1. Okay. From positive state, if you apply Hadamard, it will go back to stage 0. So you will have a exact distinction between where you applied your Hadamard gate. Are you able to understand? So any doubts? So all these 4 gates has its own inverse. Has its own inverse. It means if you apply the same gate next to next, it will cancel each other effects. Okay. So click stage 0. All of you click stage 0. Now apply Hadamard gate. Apply Hadamard gate. Apply Z gate. So what we did, we are in stage 0. We applied Hadamard. Where it will go? It will go to positive state. From positive state, if we apply Z gate, so what is the definition of Z gate? So Z gate will introduce pi rotation. Okay. So from here, if you do pi rotation, where it will go? It will go to negative state. So it will go to negative state. From negative state, if you apply Z again, what it will do? It will do pi rotations again. So it will come back to positive state. So this is how you need to understand quantum gates one by one. So what is the rule of Z gate? Only in stage 0, only in stage 0. So only in stage 0, it will act like, it will act like identity gate. So remaining wherever you are, remaining wherever you are, it will introduce pi rotations. Okay, click stage 0, click any random point, click any random point. Okay, click Z, you can observe it will go to opposite side of your sphere. So click anywhere downside, click Z gate, observe what happens, it will go to exact opposite side. So all of you able to understand X, Y, Z Hadamard? Any doubt? Okay. So now what we do? Now what we do? We try to discuss S gate. So click stage 0, click Hadamard gate, apply S gate. So I will write equation. So from stage 0, apply Hadamard, it will go to positive state. From positive, apply S gate and tell me where it will go. Put in the chat box. It will go to Y axis. Very good. So it will go to Y axis. So from stage 0, if we apply Hadamard gate, it will go to positive state. From positive state, if you apply S gate, it will go to in between positive state and positive I. So in between. Okay. Sorry. I mentioned wrongly. So what it will do? It will do pi by 2 rotation. Pi by 2 rotation. So exactly like Y gate, but without bit flip. So Y gate, what it will do? Y gate will do bit flip along with pi by 2 rotations in phase, isn't it? Okay. So what S gate will do? S gate only do pi by 2 phase rotations. So S gate is a phase gate. So it will change your signal pi by 2 rotations. So look at here. So click stage 0, apply Hadamard, it will come to positive equal superposition. From equal superposition, if you apply S gate, it will do pi by 2 rotations. So downside you can see pi by 2 value. So S gate will do a phase shift. What about the phase shift? Pi by 2 along with XY plane, along with your Z axis. Okay. So now we are in I state. So what we did, from stage 0, we applied Hadamard, it will come to positive state. From positive, again if we apply S gate, it will go to I state, Y axis. Okay. From Y, again if we apply S, where it will go? Put in your chat box. From Y, if we apply S gate again, it will go to negative state. Exactly. It will go to negative state. Very good. So what it means, if you apply S gate from I state, it will go to negative state. It means if you apply 2 S gate, will not cancel each other. Okay. So it will not go to previous position. It will go to new position. So X gate, Y gate, Z gate, Hadamard gate, if you apply twice, it will go to original position. But S gate will not go to original position, it will go to new position. So this is the important point you need to notice. You need to notice. Okay, so that is why we created additional gate. We created additional gate, which is called S dagger. S dagger. So what is the use of S dagger? It is opposite for S gate. So try to remember this, very easy, right? So what is the use of X gate? Not operation. What is the use of Y gate? Not plus pi by 2 rotation. What is the use of Z gate? It will introduce pi rotation. It will introduce pi rotation. Okay. But it won't do anything in stage 0. So I will change color. I will change color. It won't do anything. It won't do anything. It won't do anything in stage 0. Apart from all point, it will do pi rotations. Okay. So next what we discussed about Hadamard gate. It will create equal superposition. Okay. From stage 0, it will go to positive state. From state 1, it will go to negative state. Okay. So what is the use of S gate? What is the use of S gate? So S gate will introduce pi by 2 rotations. So that is the difference. Y gate along with the bit flip with pi by 2. But S gate only it will do pi by 2. Now is it clear? Now is it clear, your question? Yes. Good. Okay. So if you click S dagger from minus state, it will do opposite. Just now I told Y gate will do bit flip. So recall, click stage 0, click Y gate. Observe what happens. It will do bit flip. It changed from stage 0 to 1. Then it applied pi by 2. So this is bit flip along with the phase flip. Okay. So click state 1. Click state 1. Now apply S gate. Observe only the change in phase, not change in your state. Are able to get. So one retain as it is. But downside you can see phase shift. Now is it clear? Yes, sir. Thank you, sir. Thank you. Very good. So you can take more time about the basics of gate because gates are very important to construct quantum circuit. So if you are strong in quantum gates, you can build a wonderful quantum circuits. So that is the logic. Okay. So click stage 0, click Hadamard gate, apply S gate, it will go to Y axis. Again apply S gate, it will go to negative X axis. So apply S dagger, it will bring back to original position. Okay. Apply S dagger, again it will bring back to original position. So whatever S do, S dagger will do in opposite direction. So this is about S gate. Okay. So click 0, click 0. I will write and try to guess. Click 0, apply Hadamard, it will go to positive state. From positive, apply T gate and tell me where it will go. So put in the chat box. So click stage 0, apply Hadamard gate, then apply T gate and tell me where it will go. Exactly in between X and Y. Very good. So very good. So click stage 0, apply Hadamard, click T gate, it will go in between positive state and negative state. So apply Hadamard in stage 0, it will go to positive state. From positive, if you apply T gate, exactly it will go in between positive state and I state. So can you predict the operation of T gate? Can you predict what is T gate is doing? Can you predict? Can you put in chat box? It will create pi by 4 rotation exactly. So what T gate will do? What T gate will do? So T gate will introduce pi by 4 rotations. What S gate will do? S gate will do pi by 2 rotations. What Z gate will do? Z gate will do pi rotations. So what Y gate will do? Y gate will do naught plus pi by 2 rotations. So remember, in this way, it will be easy for you. So you won't get confused along with all these gates. Okay. So from here, if you apply T gate, it will go to Y axis. Okay. So what do you do? So we are starting from stage 0. We applied Hadamard, it will go to positive. From positive, if we apply S, it will go in between positive state and I state. Okay. From here, if you apply S gate, it will go to I state. So it means 2 S gate equal to 2 T gate, 2 T gate equal to 1 S gate. Okay. So you can compare with Z gate. Okay. So 1 Z gate or you can say 2 S gate equal to 1 Z gate. Now compare all. So 4 T gate equal to 2 S gate equal to 1 Z gate. So wherever if you want to apply 4 T gate, you can replace with just 1 Z gate. So this is the logic. So you need to reduce your number of gate operations. So you need to know all these relations. Exactly. I'll tell. Very good question. Okay. So T gate don't have own inverse. That is why we created T dagger just like S dagger. Okay. Apply T dagger, it will come to original place. So click stage 0. Click stage 0. Okay. Apply Z gate. Apply S gate. Apply T gate. Observe what happens. So it will do nothing, because these gates are phase gates. Phase gates. Okay. So click state 1, apply Z, apply S, apply T. You can observe phase rotations. So this is the beauty about quantum. So at one point, nothing works. At opposite point, everything works. So this create a randomness. Are you able to get the point? So all these gates are phase gates. All these gates are phase gates. But Y is little bit phase. Okay. It will operate on state 1 and state 0. But remaining gates won't work on state 0. That is the primary difference. So you can see variety of gates, variety of operations. So all of you able to understand why it works? Okay. So click stage 0, apply Hadamard. Apply Hadamard. You can apply all these gates. Z gate will function, S gate will function, T gate will function. Okay. Click any random point. Click any random point. So apply S gate will work. Apply T gate will work. So you can view in this way. So click here, apply S gate. It will do pi by 2 rotations. So click here. Again you observe, click T. You can observe pi by 4 rotations. So only in stage 0, Z gate, S gate, T gate will not operate. So phase gate have limitation. Only in stage 0 it will not work. So everywhere in your key sphere, block sphere, it will work. Is it clear? So any doubts? I will repeat, but listen, please listen carefully. So look at these gates. We have two states, state 0, state 1, which is equivalent to binary value. Remember in this way. So state 0, state 1 are called pure states, exactly equivalent to binary states. Okay. So if we click X, it will behave like a NOT gate. So from state 0, it will go to state 1. So this is classical NOT gate. So whatever you do in your electronics, it will do in the same way. Okay, from state 1, if you click back X gate, it will go back to state 0. Okay, so this is about X gate, not operation. So click Y gate from state 0, it will do classical NOT along with phase change. So this give a additional freedom of computation. Okay, so more hands you have, more task you can do. So this is the analogy I can give. So if you have 2 hands, you can do maximum work which is able to do by your 2 hands. Imagine if you have 4 hands, the more work you can accomplish. So that is why all Indian gods, okay, most of the popular gods, they have multiple hands. So it means they can do more work beyond a human being. So supernatural, right? So they can do more work. So this is a little depiction. So more hands you have, more work you can do. More heads you can have, more thinking you can do. Now, Y gate have advantage when compared to classical NOT? Because you can do some changes, some additional changes. Is it clear now? Okay. So Z gate, what it will do? It will do pi rotations. So in stage 0, it will not work, but in state 1, it will work. So everywhere it will work apart from stage 0. Okay. What Hadamard gate will do? Hadamard gate will do equal superposition. It will create equal superposition. From stage 0, if we apply Hadamard, it will come to positive. Okay. From state 1, if we apply Hadamard, it will go to negative state. Okay. So S gate will do pi by 2 rotations. T gate will do pi by 4 rotations. So S gate, T gate don't have own inverse. That is why we created inverse gate with the help of S dagger and T dagger. So if you understand this, so click downside, theta equal to pi by 8, and you can see multiple rotations. So Rx, Ry, Rz. So this will do minute rotations. So what X gate will do? X gate will do bit flip. Okay. So if we apply Rx, it will do operation. It will do operation little by little. So if you are applying not operation, angle by pi by 8. Look at the difference. So in classical, you don't have any degree of freedom from 0 directly to 1. But here, more you have space to do not operation. More operation means more computation you can do. Simple not operation you can see. So how many steps it will take? Lot of steps. So lot of possibility it means. Are you able to get the idea? Same way, if you click RY, it will do Y operation little by little. It will do Y operation little by little. So RZ, it will do Z operation little by little, but in stage 0, it will not work. but click state 1, apply RZ, it will work. Okay, click anywhere randomly, then apply RZ, then you can able to visualize. So if you understand all these gates, more minute you can do transformation. Okay. So we need to design. So these are the gates. So these are like tools. If you want to write algorithm, so how many possibility can do, you can select your gates, depends upon that. Okay. So click d equal to pi by 12. Now we have more finite movement. More finite movement. So infinitely, you can change your angle. So slowly you can change more degree of freedom you have. So S dagger, T dagger don't have own inverse. That is why we created, S gate and T gate don't have own inverse. So that is why we created S dagger and T dagger. So observe in this way, click stage 0, apply Hadamard, click S gate, it will do pi by 2 rotations. Again click S gate, it don't go back to original state. So that is why they created 4 gates in this side, 4 gates in this side. So that is why we created inverse. Okay. So click Z from positive, it will go to negative state. From negative, again apply Z gate, it will come back to original state. So Z here will act like opposite if you apply twice. So technically, if you have pi rotations, it will come back to original state. That is the point. Is it clear now? Why we don't have own inverse for S and T? Because it doesn't have pi rotations. So shall we move? Shall we move to next? So go to Composer. I'll share this link. If you don't have account also, you can work in this link. I'll share this link. So go to the Composer. Go to the Composer. So delete 3 Q gates and 3 classical gates. Keep only one gate. Keep only one gate. So go to View. Go to Panel. Enable Graphical Editor and QSphere. Only 2 options. So enable face angle. Enable face angle. So what I do, I try to implement NOT gate. So initially all quantum states initialize to state 0. So this is NOT gate. If we apply NOT gate, it will change into state 1. So imagine this is off state. So this is on state. So some changes will happen in your circuit, electrical circuit. So power supply will happen. So power supply will happen over here. Imagine in this way. Now your phase disk is changed to blue color. So initially it is in gray color because stage 0. Now it is turned into blue color. So imagine this blue lamp supplied with power. Now look downside from north pole to south pole, it is rotated. So this is about NOT gate. So if you apply one more NOT gate, what happens? 2 NOT gate will cancel each other. So we are starting from stage 0. So first NOT gate, here what happens? It will change into state 1. Again the second NOT gate, what happens? Again it will change into stage 0. So stage 0 means no power supply. No power supply. Now look at here, it is in gray color. So it is in stage 0. Now look at your Q sphere, it is pointing to north pole. So we discussed about empty circuit and NOT gate. Okay. So what we do, we try to implement identity gate. So it will do nothing. So if you drag and drop I gate, it will do nothing. Okay. So how many identity gates if you are putting, it will do nothing. So if you want to do some pass activity, okay, you can try I gate. Okay. So what we do, we try to implement Z gate. We try to implement Z gate. So what is the value over here? Starting with stage 0. So always remember the empty qubit starting with stage 0 in APSCHE. So what Z gate will do? It will introduce pi by 2 except in stage 0. So we already started with stage 0. So Z gate will not do anything. It will do like identity gate. It will do like identity gate. Now you can see the state is not get changed. Look at the phase angle also not get changed. So normally what Z gate will do, it will do pi phase rotations, but phase rotation not happen because we started from stage 0. Okay, to realize the Z gate, what we supposed to do, we supposed to introduce a NOT gate. Okay, so implement NOT gate. Now observe your circuit. We started from stage 0. We implement a NOT gate. What NOT gate will do? It will do state 1. Okay, across your circuit, power supply will be there. Okay, if state 1 is there, then you are implementing Z gate. It will introduce pi by pi rotations. Okay, so 1 is changed to minus state 1. State 1 is changed to minus state 1. Okay, so how we can realize this state change? So look at the phase. Look at the phase. So over here, phase angle equal to pi. So that is depicted in red color. So state change you can see from this color circle, color wheel. So what do you do? Just delete this Z gate. Just delete this Z gate and observe changes. Now there is no phase angle. Are you able to realize? Okay. What happens if you apply 2 Z gates after NOT gate? So 2 Z gate will cancel each other. Now your angle become 0. Are you able to realize? So state 1 converted into minus state 1. Again it is converted into state 1. Okay. Now delete this Z gate. Delete this Z gate. Okay. We discussed about S gate. So apply S gate over here. Apply S gate over here. Now we can see changes. So what is the change? The change is equal to pi by 2. Change is equal to pi by 2. Now color is changed to pink color, not red color. Red color is pi. Okay, pi by 2 is pink color. Magnified too much. I try to reduce. Okay, fine. So what we do? We implement one more S gate. One more S gate. So we implemented 2 S gate, which is equal to 1 Z gate. So what Z gate will do? It will introduce pi rotations. Now look this. This is similar to Z gate. So angle is pi. Okay. Now click this yes, delete. Click this yes, delete. What you can do? You can implement T gate. So whatever we discussed in previous blocks here, we try to check all these gates. So apply T gate. Now observe what happens. it will introduce pi by 4 rotations. It will introduce pi by 4 rotations, which is in violet color. So apply 2 T gate and it is equal to 1 S gate. Apply 2 T gate, it will equal to 1 S gate. Now angle is pi by 2. So all of you able to follow, I hope so. Okay. So instead of NOT gate, what we'll do, we'll implement Hadamard gate. So this is very important gate. Okay. So what Hadamard gate will do? Hadamard gate will create equal superposition. So it means it will generate 0 sometimes. It will generate 1 sometimes. Okay. Randomly it will generate. So it will generate randomly. So output is not fixed. Output always changes and you cannot predict what is the output in next iteration. Suppose if you are running for 100 times, if you are running the same circuit for 100 times, okay, so you will get 50% of the time value as 0, 50% of the time value as 1. So if you want to generate a random number, what you can do, you can generate Hadamard gate. You can implement Hadamard gate. So this is a simple circuit to produce one random bit. So this is a simple circuit to produce one random bit. Okay. So if you want to know the value, what you're supposed to do, you need to do measurement. So I'll zoom for your convenience. So this is called measurement gate. So we have Q0 started from stage 0. If we apply Hadamard, it will create equal superposition. Okay, it will go to equator exactly in positive state. But if you apply measurement, your output is totally random. So sometimes you'll get binary value 0 in classical register C1. Sometimes you'll get binary value 1 in C1. So C1 is your computer, classical computer or classical RAM, you can say in this way. Okay. Now you can see the superposition state is collapsed because whenever you do measurement, superposition state will get collapsed. So all of you know the meaning of superposition, or you want me to repeat? Is it covered? Put in chat box. All of you understand the meaning of superposition, or I want to take one more time. Okay, already covered once. Okay. I'll take, no issue. Yes, topic is very, very important. So covering topic is not important. Understand that concept in depth is very important. So I'll explain superposition and entanglement in a short time. So superposition, if you want to define superposition, again you need to take classical analogy. I'll tell, please wait. I'll share PPT, don't worry. So take an example of a coin. If you are tossing a coin in the air, so your coin is in between middle of your air. Okay. So you cannot say what is the state of your coin. Okay. Because the coin contains two sides. One is head, one is tail. Okay. During the air flip, okay, the position of your coin is 50-50%. 50-50%. So 50% of the time your coin is facing to head, 50% of the time your coin is facing to tail. Okay. So when you can say your coin is 100% facing head or 100% facing tail, you need to do measurement. You need to do measurement. So what you can do in two ways. You allow that coin to settle down in the ground. Then you can observe after some point of time. Then you can say 100% it is head, 100% it is tail. It is natural measurement. Okay. So once you do measurement, allow that coin freely flow over the ground. Then you observe. Okay. Then observation will reveal the state of your coin. Otherwise, what you can do, you can forcefully stop that coin by your hand. You can stomp that coin. Then you can open your hand. Then you can observe. So two ways you can do measurement. Okay. So anyway, if you do measurement, superposition state will get collapse. So this is the idea. Okay. So you can correlate this example to Erwin Schrödinger cat. It is a thought experiment. So it is a black box. Okay. Inside a black box, you are keeping a cat, alive cat, and a radioactive material. So nobody in this world able to predict when this radioactive material going to decay. If it is decayed, cat is exposed to radioactive material. If it is exposed, cat will become dead. So there are two chances for a cat inside that box, either being alive, either being dead. Inside that box, you don't know what is happening. Okay. So that is why you can describe the state of a cat. 50% it is in alive state, 50% it is in dead state. Okay. When you open this box, what you are doing measurement. You are doing measurement. Once you do measurement, what happens? Superposition state will get collapse. Superposition state will get collapse. Either you can see cat alive as 100%, or either you can see cat in dead position for 100% sure. Just like looking at your coin, tail 100% or head 100%. Okay. So when you do measurement, what happens? Superposition state will get collapse. We'll get only one possibility. Okay. So try to increase complexity of example. Now what we are having, we have cube. Cube contains 6 faces, each face color with different color. Okay. So which face appear front for you? Orange or blue? Put in the chat box. Which face appear front for you? Orange or blue? Orange. Very good. So if you are observing from this face, wait. If you are observing from this angle, orange appears like front. If you are observing from back side, blue appear like front. So I am not added from which side if you are observing. So according to the angle, the result will vary. Are you able to get the idea? So 6 faces means 6 equal probability. Right? So try to relate this example with electron. Consider electron like a cricket ball. Sometimes it will spin upwards, spin downwards. If it is spinning upwards, try to map with state 0, binary value 0. If it is spinning downwards, try to map with binary value 1. So sometimes cricket ball can wobble. Okay, it will wobble. So if it is wobbling, it is in superposition. At the same time, you can represent both 0 and 1. Because it is in superposition. So superposition means one position over another position. But if you do measurement, superposition state will get collapse. You will get only one possibility. So here you have 6 possibility. But if you do measurement, you will see only one side, only one color. Are you able to get the idea? So this is about superposition. And try to look at entanglement. So entanglement is a strong correlation between two quantum particles. Okay, so look at this example. Under the right condition, only this plant will go to its full potential. In the same way, under the right lab conditions, sorry about that, under the right lab conditions, you can take two electrons, or you can take two photons, or you take any two subatomic particle, you can create strong correlation among them. You can create strong correlation among them. Then you can say it is a entangled particle. So this process is called entanglement. Okay. So what is the meaning of entanglement? There is a strong correlation among two or more particles. So take an example of friends. Take an example of friends. If friends are doing some mistakes, or friends are doing any anything, okay, if friend one is supporting for team A, so friend two also support team A, because they are strongly correlated, they are positively correlated. So whatever the first person is saying, the second person always agree. Okay, take an example of enemy. So first person and second person, whatever the first person say true, the second person always say opposite to that, false. So this is how normally everywhere I can see this phenomena. Okay, if there are two opposite party, ruling party, opposite party, they always go against each other. Okay, so in national issue, in any case of war, all these party will come to one point. They will support each other under a common goal. Okay, so what you can do, if you're taking two subatomic particle, it could be electron, it could be ion, it could be proton, it could be any subatomic particle. Once you make a strong correlation, then what you can do, you are able to separate those particles. So keep one electron in Earth and move another electron to moon or satellite. So whatever you are doing for one particle, the same effect you can see in another particle, because they are strongly correlated. So this is useful for communication. This is useful for communication. So entanglement is useful for multiple purpose. So one purpose, important purpose, is quantum communication, because they are strongly correlated. So if you want to understand entanglement, you can go through this example. So rock, paper, scissors. Okay, if three players are playing this game, okay, instantly you can measure one decide state of other participants. So only one person is winning, the other person is losing. Okay, so this is an example for entanglement. So take an example of playing cricket, playing football. It will take lot of time, but rock, paper, scissors, instantly you can declare the result. Okay, so this is an example. This is particle 1, this is particle 2. We are making strong correlation. Okay, imagine positive correlation we are making, friends. Okay, so we are separating these two particle 1 in Earth, particle 2 in some other galaxy. Imagine in this way. And what we are doing, we try to rotate particle 1 to downside. Particle 1 to downside. Now it is pointing to South Pole. So what is the meaning of South Pole? We map to state 1, binary value 1. Okay. So if we are measuring the particle 2, this also shows state 1. So this is like communication, right? Suppose The next time, if you are rotating particle 1 to north pole, so it denotes 0. So here also you can see the same effect. This will move to state 0. So this is how communication happens. Okay. So imagine if we try to rotate this one to north pole, this also moves like a black magic. So whatever happens for particle 1, you can see the same effect in particle 2. So whatever you do for particle 2, you can see the same effect in particle 1. So this is called entanglement. So we covered superposition and entanglement. Okay, we covered superposition now. Now delete this measurement gate. Again, you can see superposition. So once you do measurement, superposition state will get collapse. Right? Now delete this Hadamard gate. Click here, increase 1 qubit, increase 1 qubit. So in same way, increase 1 classical bit. So do in this way. Are you able to follow? So click qubit, click plus. If you click plus, it will add 1 more qubit. So 2 qubit, 2 classical bit. So far we discussed only single qubit. Now we are about to see 2 qubits. So all of you able to follow? All of you came to your composer. Shall we start? Hello? Please put in chat box. Am I audible? Is my screen is visible to you? Great. Okay. Okay. Now look at here. Okay, enough. Look at here. We started from stage 0. Now both qubits are in stage 0. That is why you got 0, 0. So move your mouse over here. You can see 0, 0. Now you look at your block sphere, Q sphere. Now you can see some changes. Now you can see stage 0, 0. Initially it is only stage 0. Now you got stage 0, 0 because we contain multiple possibility. So if we add 1 more qubit, you will have immense representation. So this is beauty in quantum. Okay. Now what do you do? Drag and drop NOT gate in Q0. So this is stage 0. Okay. This is NOT gate. What happens? It will move to state 1. Okay. So you'll have power supply over here. Okay. Now you can see the output as 0, 1. So this is state 1. This is state 0. That is why in block sphere, you can see changes. Now it is moved to right hand side. Are you able to see the changes? Now it is moved to, left hand side. Okay. A composer, I will share that link. Don't worry. So I will share in the chat box. So always bookmark these links. So we'll discuss entanglement later in upcoming class. We don't have time. We'll cover first these gates. So go to view, go to panels, enable state vector. Enable state vector. Okay. So click this NOT gate, press delete. Click this NOT gate, press delete. You can see it is pointing to stage 0, 0 because circuit is empty. Suppose if I am implementing NOT gate in Q0, Now we can see changes in your state vector. Now what it means? Q0 is mapped to rightmost bit. Okay, so Q1 is mapped to leftmost bit. So this is little confusing in QuizKit because they rearranged in this way. So note down this point, otherwise you will get confused. So always topmost qubit map to rightmost bit downside. Okay, so here the bottommost qubit is mapped to leftmost bit. So that is why it is pointing to 0, 1. Look at your Q sphere, it is pointing to left hand side, 0, 1. Now what do you do? Drag and drop this NOT gate to Q1. Now you can see the changes. It is moved to 1, 0. It is moved to 1, 0 because Q0 is pointing to rightmost bit. Q1 is pointing to leftmost bit. Now what do you do? Drag and drop one more NOT gate. Now it is changed to 1, 1. Now it is changed to 1, 1. Are you able to follow? Because initially it is pointing to state 0, 0. Now look at your Q sphere. Now it is pointing to south pole. Okay. So what is the extreme for south pole? North pole. So what is the value associated with north pole? State 0, 0. What is the value associated with south pole? State 1, 1. Okay. So in this way you can recognize. So in left hand side, what is the value they depicted? 0, 1. So in right hand side, what is the value they depicted? 1, 0. So these two are opposite. So look at here. These two are opposite. Okay. These two are opposite to each other. Now we discussed single qubit gate. We discussed 2 qubit. We implemented NOT gate in 2 qubit. We explored all possible combinations. Okay. Very good. Now what we do? We try to cover C0 gate. So this is nothing but C0 gate. Okay. So in another term, you can say controlled NOT gate. Controlled NOT gate. So this is like soldering. So this is like soldering, or you can say tapping. Okay. So we are tapping the connection from Q0 to Q1. So this is like power supply wire. This is like power supply wire. This wire is fed to a NOT gate. So this is your NOT gate, normal NOT gate. So this NOT gate depends upon power supply from Q0. Okay. So this gate will act the first one as control qubit. Control qubit. So what is your control qubit? Q0. Okay. The second qubit is called target qubit. Target qubit. So this is Q1. So note down this point. So C0 gate is called control NOT gate. Okay. The power supply is supplied from control qubit to do some operation in target qubit. So what is the operation we are about to do? We are about to do NOT operation. Now look at your output. Now look at your output. This is stage 0. This is stage 0. Okay. So no power supply. Here no power supply. So here also no power supply. So here also no power supply. It means the state will retain as it is. The state will retain as it is. This NOT gate is inactive because no power supply. So consider NOT gate is like a electrical appliance. If there is no power supply, no NOT operation is operated. Okay. To understand this, what we supposed to do? We supposed to implement a NOT gate before this. Okay. So now carefully watch stage 0, stage 0. Okay. So here we implemented NOT gate. What NOT gate will do? It will do bit flip, state flip. So power supply will happen in this wire. Okay. So this power supply will also comes down. Now this NOT gate is activated because we supplied power from control qubit. So if it is activated, the state 0 is converted into state 1. State 1 means here also you will feel power supply. Here also you will feel power supply. That is why here also you get state 1, here also you get state 1. So if you implement one NOT gate in Q0, you'll get power supply at both. So it is like AND. It is like AND. If power supply is in Q0, also in Q1. Are you able to understand? Now what do you do? Drag and drop NOT gate in Q1. Now analyze this circuit. So what happens? So here stage 0, here stage 0. We implemented NOT gate, first NOT gate, then implemented second NOT gate. So it will convert into state 1. Okay, so power supply will happen in first qubit. So it will come in downside also. So after this NOT gate, you'll get state 1. Okay, again you are giving power supply for third NOT gate. Third NOT gate. What happens? It will convert state 1 into state 0. So state 0 means no power supply. So it is opposite to each other. It is opposite to each other. If first qubit is 1, the second qubit is negotiated because we implemented NOT gate in Q1. NOT gate in Q1. Okay. So delete this. Delete this. Delete this. Delete all these gates. Implement Hadamard gate. Implement Hadamard gate. Now look at here. What happens? Sometimes it will generate 0 as the output. Sometimes it will generate 1 as the output randomly for only Q0. What about Q1? Q1 always generates state 0. So we have two possibility for Q0, but only one possibility for Q1. So how many combination you can form out of these two qubits? Only two qubits. Sorry, two states. So look at here. So state 0. Okay, state 1. This is always state 0. Okay. So this 0 possible by this 0. Okay. So this one is possible by, sorry about that. So this 0 is possible by, so 0, 1. This 0 is possible by this one. And this 0 is possible by Q1. So this is possible. Okay. So look at the second example. I will try to vary color. Okay. So this one is possible by Q0. Okay. So this 0 is possible by Q1. Is it clear? Fine. So next what we do, we try to change color. So this 0 is possible by Q0. This 1 is impossible by Q1. Because Q1 always produce 0. So this one is impossible. That is why this is not generated. So in the same way, this also not get generated. I will clear this. Now try to recall. Why we got only 0001? Because we implemented Hadamard in Q0. For Q0, 0 is possible, 1 is possible. But for Q1, only 0 is possible. So only 0 is possible for Q1. So that is why you can point 00, 101 at the same time in Q sphere. Now drag and drop Hadamard in Q1. Drag and drop Hadamard in Q1 and try to observe this output. Are you able to get or any doubt? Now work out in pen and paper. So draw the circuit, try to predict the output. So we can go slowly. So if you have any doubt, you can put. If you're able to understand, please put the message. Okay. So we try to understand. So this is stage 0, but here it will produce 0 as plus 1. Okay. For this 0, it is possible by Q0. Okay. For this 0, it is possible by Q1. I'll try to change color. Okay. So this 0 is impossible. This 1 is impossible by this Q0. Okay. But this 1 is, this 0 is possible by Q1. I try to change color. So this 0 is possible by Q0. Okay. This 1 is possible by Q1. So this is possible. So in same way, the first qubit is not able to produce 1. So this is impossible. This is impossible. I try to clear. Now you look at the block sphere. It is pointing to North Pole and right hand side. 1, 0. Now I will make little twist. Add one more Hadamard gate in Q0 and look at your Q sphere. So 2 Hadamard gate will enable all superposition. Now we will have 4 possible combination. So 0, 0 is possible, 0, 1 is possible, 1, 0 is possible, 1, 1 is possible. So simultaneously, you can represent 4 bit string using 2 Hadamards. Is it clear? Everybody able to follow? Right? Next, what I do, I try to delete one Hadamard gate. I try to put one control NOT. Now look at the circuit and output. So what happens? Sometimes it will produce 0, sometimes it will produce 1. So you have 2 possibility. You have 2 possibility. Okay, I try to crop this image. I try to crop this image. So I want to introduce one more tool, open board. So it is a open source tool. So you can use for your class, very useful. So I copied a clip. Here I can resize about how much I want, whatever I want. So I need to explain the circuit. So we have two cases. So I can copy, I can paste this image. So this is as simple as like this. Okay. Now we will discuss. So what is the option for Hadamard? Sometimes it will produce 0. Sometimes it will produce 1. Imagine in this way. Okay. So case 1, if Hadamard produce 0. So what happens if it produce 0? There is no power supply. There is no power supply. So power supply will not be there. Okay. If power supply will not be there, it will not come down. So this NOT gate is inactive. So we are starting from 0. We are starting from 0. Okay. But here you'll get stage 0 as well as stage 0. But look at here. We have stage 0. We started with stage 0. We started with stage 0. If Hadamard gate produce 1, case 2. If Hadamard gate produce 1, then it will create power supply. It will create power supply. So this will come down. This will come down. This will enable this NOT gate. This will enable this NOT gate. So this stage 0 is converted into state 1. So here also you'll get power supply. So here also you will get 1. Here also you will get 1. I hope this is easy for you to understand. So Hadamard gate produce 2 distinct output. So each time it will vary. Suppose if your circuit generated 0, okay, for first qubit, the second qubit also 0. If first qubit is 1, the second qubit is also 1. So this is equivalent to entanglement. Very good. So this is equivalent to entanglement. So look at here, state 0, 0, state 1, 1. So the first particle is 0, the second particle is also 0. If first particle is state 1, the second particle is also state 1. So this is positive entanglement, like friends. Okay. So how to make the circuit in opposite way? If first qubit is 0, the second qubit need to be represent 1. How will you do that? So please put in chat box. How to change your outputs, opposite, total opposite. No need to put another control NOT. Simply produce NOT gate. So put NOT gate in Q1. So automatically you will get opposite values. So first qubit value is 0, the second qubit value is 1. If first qubit value is 1, the second qubit value is 0. Now the pattern is get changed. Are able to understand? So either you can put NOT gate before control NOT gate or after control NOT gate, you will have the same effect. You will have the same effect. Okay, fine. So go to view, go to panels, enable code editor, So go to view, go to panel, disable state vector, go to view, go to panels, disable Q sphere. Now we can see only circuit along with your code. So initially it is pointing to open QASM. So click here, try to change APSCHE. You'll get equivalent Python code for your circuit. All of you able to do? So go to view, go to panels, enable only graphical editor and code editor, disable everything, and resize your window in such a way. Okay, so select all these gate, click, press delete button. So click in the circuit, then do, otherwise it won't allow you. So this is your empty circuit. So click here, delete bin button. So click here, select minus button. Keep only one quantum bit, only one classical bit. I will make little zoom for your reference. Make only one quantum bit, only one classical bit. So look at your code. Look at your code. So from QuizKit, import quantum register, classical register, quantum circuit. It means this is your library. This is your modules. So from library, only 3 modules are imported. Okay, if you don't know programming, if you are from physics, chemistry, maths, please discuss with computer science faculty or student. They will help you. Okay, so from NumPy, so this is a mathematical package. Okay, from NumPy library, we are importing pi module. So we will import pi value. So look at line number 4. What we are doing, we are calling quantum register function. This is a function call. So for this function call, we are passing parameter. So 1 means 1 quantum register. Q means it is a label given for this register. Okay, which is stored under Q register underscore Q variable. So this variable contains quantum register. So in same way, line 5 contains classical register. Okay, so line number 6, what we are doing, we are creating quantum circuit with number of quantum register with number of classical register. Okay, so you can imagine we are passing 1, 1. So what is the value over here? So you can imagine in this way. So this is nothing but 1, 1. So quantum circuit 1, 1 will generate this circuit. Okay, so what is the name of your circuit? Just circuit. So these 3 are variables. These 3 are variables. Okay, so these 3 are called function call. Function call. So non-computer science people, don't get panic. Okay, just try to understand. From this circuit, you're able to generate code in this way. Empty circuit, right? Now what we do, we try to implement NOT gate in Q0. It will generate code for you. So this is your circuit. This is your circuit. I'll zoom for your convenience. So you've implemented NOT gate, automatically your code is get updated. So look at line number 8. What we did, circuit.x. So within parentheses, we are giving Q register underscore Q 0. It means we are implementing NOT gate. NOT gate is X. We covered in block sphere, right? Try to recall. So NOT gate is depicted by X. So we implemented X gate in Q0. This is the meaning. Okay. So what we do, we try to apply Hadamard gate after NOT gate. So you can see the sequence. So what we did, we applied Hadamard gate after NOT gate. So line number 9 is appended automatically. So if you don't know programming, just observe what is happening in the background. Okay. So rechange the sequence, drag and drop Hadamard gate before NOT gate. You can see coding sequence get changed also. So first implement Hadamard followed by X gate. Okay. So delete this NOT gate. Now try to implement measurement gate. So we did measurement, right? So what is the coding for that? circuit dot measure Q register 0, C register 0. It will create the data flow from quantum to classical bit, quantum bit to classical bit. So we have 1 qubit, 1 classical bit. That is why 0, 0. Okay. So what we do, we'll delete these gates. So click this, press delete button. Okay. What do you do? Click one more qubit, click one more classical bit. Now see the changes. Now the parameter changed to 2, 2. So this is how you need to realize whatever you do in your circuit, code is get reflected. Okay. So apply Hadamard gate in Q0, apply control NOT in Q1 and Q0. Okay. You'll get coding in this way. Okay. So apply NOT gate. So NOT gate in Q1. So this will create opposite entanglement, right? So this will create opposite entanglement. Now look at the sequence. We applied Hadamard in Q0. We applied NOT gate in Q1. Then we applied CX2, Q0 and Q1. So this is 2 qubits. That is why we gave 2 parameters. So Q0 will act like control. Okay. Q1 will act like target. I hope everybody able to follow. So you can do all this programming in Google Colab. I'll tell how to install. So go to Google Colab. If you have Gmail account, you can go to Google Colab. I'll share this link to you if you are from non-computer science background. I use Zoom for some easy understanding. Whether this Zoom effect is reflecting. So all of you go to Google Colab, go to File, go to New Notebook in Drive. So it will generate a Python notebook for you. So this is your Python notebook. So whatever you do over there, whatever you are doing there, we are able to do by code. So I'll share this link with you. So this is how you need to install QuizKit in Google Colab or Jupyter Notebook, whatever you are having. If I am not using Zoom, sometimes the audience will feel difficulty. Okay, Zoom will help. That is why I am using. So you can use this command. You can use this command if you want to install in Windows. Okay. If you are using Linux, you can click this tab. If you're using Mac OS, Apple OS, you can use this one. According to your system, you can use. Okay. So this is the command. Just copy pip install QuizKit. So click here. So click here, paste over here, press enter, shift enter sometimes. It will install QuizKit library for you in this package, Python notebook. So successfully installed. The latest version is 2.2.1. So same way you copy this, install in the next box. So automatically this box are get generated. What you do, press Shift plus Enter. So it will install IBM runtime. So no need to have credit card for this. So you can do simulation without doing any credit card. So just your Gmail account is more than enough. Okay. Then what you do, you can go to this. You can go to Composer. Okay. You can copy code from here. Yeah, you can install in Jupyter Notebook also. No issue. Very good question. Same procedure. So press Shift plus Enter and check whether it is working. From my end, it is working. From my end, it is working. Okay. So how to visualize your circuit? So you need to do circuit draw. So circuit dot draw, you will get output in this way. So I'll share this code with you. So whatever the logic you are using, you're able to get the output. So this will give output in this way. So this is how you need to code. So GUI only for understanding purpose, for beginning purpose. After some point of time, you need to definitely move to coding part. So whatever we discussed, you try to make code in this way and try to execute and try to visualize. So I can visualize circuit in different way with the colorful method. Draw MPL. So I'll share this link with you. So we will cover in next session if it is possible. So go here, click here, paste over here, Shift Enter. Sorry, I mistakenly gave QC. This is circuit. So for that, we need to install visualization tool. I missed that. So one shot I will share with you. Okay, it is keep on asking for library. So whenever it gives any suggestion, install in same way. So Again, some package is missing. Okay. They have so many updates. I cannot figure it out right now. Okay. MPL install, I will check. Not about MPL, matplotlib library. No, it is not working. Okay. It should support. Yes. Okay, I'll rectify these mistakes. In next class, I will tell you what is the fix for it. So if you have any doubt, you can ask me. We'll wind up now. Thank you all for patiently listening. So I try to cover as much as possible.
Sir, and
Thank you, sir.
participants.
Thank you.
Thank you very much for the very important session. They have been listening to the theories, but now they're hands-on, which is very much important for them. So we thank you. So participants, I hope that you are enjoying. I can see that participants are actually. So thank you for all participants also. So thank you. And regarding quiz, do you want to? Okay. So we'll announce that in the weekend.
Saturday, Sunday, Monday.
Right. So Saturday, Sunday, Monday will be opening up quiz to participants. I will. The future class to home for guiding the participants on this hands-on.
Yeah, actually, the material, so don't worry. At the same time, please go back to the videos. Sir has already very slow explained everything. So please go back and listen to the video and then do it accordingly. And of course, there is a lot of help material on Qiskit site also. You can, there's a Qiskit community asking, then you get that. Jaycon sir will send the material, please don't worry. Today, yesterday's class and today's class will upload, right? And Anita madam has not yet sent. Once she sent, she will upload, right? Yeah, there will be some errors. Please search for the codes in the Google and try to look at what are the basic things that tomorrow. Definitely, you can once again look at boards. You can share with sir, and sir will maybe discuss tomorrow. One or two tomorrow.
So we will also suggest the participants to go back to the YouTube video so we can pause the video and watch each of the steps that has performed. If you have missed any error, I think some of them are saying that they are scared. So please, you can. So I think everything for today.
Yeah. Anil sir, anything you would like to add?
Sir, good evening. Jaikumar
Evening,
sir.
sir.
Good evening.
Doctor sir. Sir,
Yes.
a personal request for you. Kindly go through that curriculum for UC Quantum, sir, major. I have shared the.
Okay.
Right,
For me, sir.
Yeah. This question is for you.
Yeah. Sure. I'll do that.
So
Thank you.
UC major,
Yeah, I'll look at it.
we finished UC minor for quantum.
Yeah. Now,
So
UG
I
major
shared
we
the
have to-
draft,
we'll-
and you please
we'll do that.
share your inputs.
I'll sure.
Thank you, sir.
Thank you, sir.
Thank you, Dr. Jaikumar. We'll continue with Jaikumar sir till Monday afternoon. So please be one lecture. Then we send file and Tuesday revise the final schedule. Conclude with one more quiz at the end of the course. Please complete certificates after the we'll give the certificates. Yeah, thank you so much. And 27th, using that. But tomorrow or day after, I will share the schedule and registration process. You can try to complete, right? So that's the thing, right? Yeah. Okay. Yeah. The others who are still asking questions, please reserve your questions. Sir is there with us tomorrow. You can at the beginning, sir will give you some time where you can ask the questions, right? Thank you.
Thank you, sir.
Thank you, everyone.
Right, sir. Thanks.